All right, focus for today's lesson, standard deviation. First slide. The most common measure of spread looks at how far each observation is from the mean. This measure is called the standard deviation. Consider the following data on the number of pets owned by a group of 9 children. So we have a dot plot given here. So we have one kid that's got 1 pet, one kid that's got 3 pets, 1, 2, 3 kids that has 4 pets, etc., etc. And he already calculated the mean for us. The mean for this data set is 5. All right, the deviation, how far away are you from that mean? So for this point right here, it's 4 less than a mean, so its deviation is -4. This point right here is 3 more than a mean, its deviation is 3. The standard deviation, and the notation for this is S sub x, measures the average distance of the observations from their mean. It is calculated by finding an average of the squared distances and then taking the square root. The average square distance is called the variance. All right, squaring and square rooting within the same statistics problem is relatively common. That's a strategy you can use to get all your values to be positive. Okay, specifically how it's used here. First, we're going to get variance. Variance is the square of standard deviation. Okay, x sub 1, x sub 2, blah, 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 blah. They represent each individual data point. So we're going to take the individual data point, we're going to subtract the mean, that gets squared. Take the second data point, subtract the mean, that gets squared, etc., 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 and then all those guys get added up, and then ultimately we're going to divide by n minus 1. So the way that we use the notation to describe this is that's the capital Greek letter sigma. So it's the sum of all these individual things right there, and dividing by n minus 1 is the same as multiplying by 1 over n minus 1. So the formula, as it typically appears, is right here. Now, a question that usually gets asked at this stage is, why are we dividing by n minus 1 instead of n? At this stage of the course, it's beyond what is necessary to discuss in detail. It's not something you're really going to have to worry about in terms of why it works. We're going to kind of file that under, it is what it is. There are times we divide by n versus n minus 1, and we're going to touch upon that a little bit later in the presentation. All right, so how would this work out mechanically to go through this formula? So this is the same dot plot from the first slide. We were already told that the mean is 5. So each individual data point, we have the 1, 3, 4, 4, 4, the 5, the 7, the 8, and a 9. So working through this here, each individual data point is going to have the mean subtracted from it. So it has all those individual data points minus 5, and that gives us our deviations. Okay, then those differences have to get squared. Each one of these numbers here, we're going to square, and it gives us that list right there. Okay, this says that we're going to sum them all up. So the sum of all those is 52. And then the last step is we're going to multiply that by 1 over n minus 1. N refers to the number of data points. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 data points. So we're going to take that 52 and multiply it by 1 over 8 or divide it by 8. Either way you want to think about it, it takes us to the same place. So the variance is 6.5. We're going to do stuff with variance later in the course. For now, variance is just a stepping stone to get to standard deviation. Once we have that value, we're taking the square root of that thing that we just calculated. The square root of the variance is the standard deviation. That's the key number, the 2.55. All right, so for this slide, this is the same line plot. We were told the mean to start with. We just calculated the standard deviation. A very common question you're going to be asked for free response questions are interpreting that standard deviation in context. Well, everything we do is in context. If it says interpret standard deviation on the AP exam for real, it's probably not going to say in context. It's assumed everything we do here is in context. So the wording we're going to use, the number of pets typically varies from the mean of 5 by about 2.55. So and then we have to have, well, what's the context of this problem? This dot plot is all about the number of pets. Varies from the mean. That's always going to be there regardless of the context of, state whatever the mean is, by, about, or approximately. That's an estimation. It's not an exact number. Whatever the number is, and then what does it represent? Pets. So all those little pieces need to be in there to check all the boxes for full AP credit. Okay, back to this for a moment. It is highly unlikely, if ever, you're going to have to do these standard deviation calculations by hand. We're going to go through calculator keystrokes a little bit later here, and that's going to be primarily what we use. You need to be able to understand formulas like this. You have to be able to read it and understand what it's doing. There could be something where they're asking you a what-if question, interpreting what's going on in here. There could be something like which set of calculations would correctly give you the standard deviation. So it's not as if we can completely ignore this in terms of the raw formula, but the full-fledged brute force calculations, highly unlikely you're ever going to have to do them in here. All right, typically, the average, so to speak, AP question is going to more be concerned with conceptually, what does it tell you? What are its properties? So more important than the details of calculating standard deviation are the properties that describe the usefulness of standard deviation. So these are some things that you should know to address that idea. Standard deviation measures spread about the mean and should only be used when the mean is chosen as the measure of center. So previewing something we're going to talk about in a slide or two, it's possible you choose median for your measure of center, or it's possible you choose mean. If you're going to use mean, then you always want to pair that with standard deviation. Okay, standard deviation is always greater than or equal to 0. Okay, going back to the formula, where is that at here? That last step of the formula is we're taking the square root of something. Unless we're in an imaginary number system, which we're not. In this class, we're always real numbers. The smallest this can ever be is 0. You can't have a negative standard deviation if you're taking the square root of a real number. Okay. It could be 0 only if there's no variability. This happens when all the observations have the same value. Otherwise, S sub x is going to be greater than 0. As the observations become more spread out about their mean, S sub x, or the standard deviation, gets larger. Okay, standard deviation is becoming more and more popular on the SAT test. And knowing that little sentence right there is good enough to get you through most SAT questions that address standard deviation. Key thing here is the more spread out the data is away from the mean, the larger the standard deviation. The more clumped in it is towards the mean, the smaller the standard deviation. Okay, in terms of keeping things in context, you always have to have units when you're answering questions. Standard deviation has the same units of measurements as the original observations. So for that previous example, the observations were a number of pets, so standard deviation is a number of pets. For example, if you measure metabolic rates in calories, both the mean and standard deviation, S sub x, are also in calories. This is one reason to prefer standard deviation to the variance, which is in squared calories. So going back to that first example, the variance would be in squared pets. So unless you have like little cubes as your pets, it doesn't really make any sense. Where we are right now, I think I mentioned it a little bit earlier, variance doesn't have much of a purpose for us other than to get to standard deviation. It turns out that you can do some mathematical operations with variance that you can't do at standard deviation, and that's going to be the key thing that's important to us when we get to that point of the class. Okay, like the mean, Standard deviation is not resistant. A few outliers can make the standard deviation very large. And we're going to address that in a little bit more detail, I think the next slide or soon after that. All right, now getting towards the calculator keystrokes, which is going to be the main thing we're going to be using to get standard deviations. Okay, many calculators, specifically the TI-83, 84 family, are going to report two standard deviations. One is usually labeled, that's the lowercase Greek letter sigma sub x. That's the symbol for the standard deviation of a population. This standard deviation is calculated by dividing the sum of the squared deviations by n instead of n minus 1. So this is getting at, sometimes you divide by n, sometimes you divide by n minus 1. If it's a population, you're dividing by n, which means your standard deviation gets that symbol. If it's a sample, you divide by n minus 1, which means your answer for the standard deviation is going to get that guy right there. All right, for where we are right now in the course, we're dealing with samples. Most often the data we're examining comes from a sample. In that case, we're going to be using the S sub x. So in Chapter 1, we're always samples. We're always using S sub x. We're always dividing by n minus 1. Next chapter, we're going to get into populations, and we'll deal with that when we get there. So, tying the symbols together. X sub bar, that's a symbol for mean, and that's when we're talking about the mean of a sample. And for now, that's what we're dealing with, samples. If you're dealing with the mean of a population, that's the lowercase Greek letter mu. The mu is what you're going to refer to or use to we'll start that over. When you need to refer to the mean of a population, that's the symbol that you use. Right, now, as far as formulas go, whether it is a sample mean or a population mean, it's the exact same formula. It's just putting the correct symbol to the number. In contrast to what we just talked about above, if you're talking about standard deviation, not only are two different symbols, there are two different formulas. So that's a detail or a set of details you have to make sure you pay attention to. So we can summarize some of these ideas here in this little table. If you are talking about a sample, the mean of the sample should always be reported with that symbol, the X bar. The standard deviation of the sample should always be reported with the S sub x. If you're dealing with population data, the mean should be the symbol used for, mu should be the symbol used for mean, and that's the standard deviation symbol for the standard deviation of a population. These two formulas are identical, no difference. These formulas are different. For a sample, you're dividing by n minus 1. Population, you're dividing by n. Now, those of you that had already had Algebra 2, you may have done some stuff with standard deviation. This table here and how we define standard deviation above, this is a little bit of a contradiction of your Algebra 2 textbook. The big picture here is we deal with statistics from a purely, as it should be in the ideal world, statistics that is considered more or less universal. What happens is when you apply the statistics to specific subjects or specific areas, like for example, those of you that are in AP Bio or already took AP Bio, you might find some differences in the way things are explained and dealt with. So there's some modifications and liberties you can take when you start applying it to certain fields. As far as comparing this to what's in your Algebra 2 textbook, your Algebra 2 textbook takes some liberties that we can't take in here. All right. When we want to describe a data set, we want to choose a measure of center and a measure of variation, or how is the spread? I'm sorry, I lost the word. The variation or the spread. The two typical measures of center you're going to choose are either the mean or the median. Okay, if you choose to use the mean, the spread that you need to pair it up with is standard deviation. If you choose to use the median, The spread you have to pair it up with is the interquartile range. And we addressed interquartile range a couple days ago. All right, now in terms of which is better when, the median and IQR are usually better than the mean and standard deviation for describing a skewed distribution or a distribution with outliers. We want to use the mean and standard deviation only for reasonably symmetric distributions that don't have outliers. Sometimes you can get a gray area. Well, where's the line between reasonably symmetric and skewed? Well, that can be a matter of opinion. If it's a free response question, as long as you're justifying it with something like, I believe that this data is too skewed in order to use mean and standard deviation, I'm choosing to use median and IQR. Or you can say that there's some slight skewness, but I don't believe it's extreme enough to prevent us from using mean and standard deviation. So as long as you have a justification and you're incorporating into that justification your knowledge of the topic, it's probably going to be acceptable. Now, if the only thing you're dealing with is numerical summaries, you can't always tell the whole picture. So when you can, you always want to plot your data. You don't always have raw data to plot, but when you can, that's something you should take advantage of. So a quick summary here of some basic ideas here. The median and the IQR are resistant to extreme values and outliers. So when you have extreme values and or outliers, that's what you want to use. Okay, mean and standard deviation are not resistant to those. So you're going to use those when you don't have the values, extreme values of the outliers, or you want to use mean and standard deviation when you have reasonably symmetric data. All right, in your textbook, the idea of the four-step process is introduced in roughly the same area that it talks about the standard deviation and variance. I forget exactly where it falls. I'm only taking note of this, or making note of this, that your book is going to refer to that like forever. It's throughout the book. If you have any level of complexity to the problem they're asking you to solve, they're going to organize it using the four-step process. When you answer a question in order to get full AP rubric credit, you don't have to label it state, plan, do, conclude. I mean, that's just what your book does, help you organize it. As long as all the things that are being addressed here are addressed in a logical order, it doesn't necessarily have to have that label. All right. Last thing we're going to be doing here. How do we calculate this stuff using a graphing calculator? And what I want to start off with is, well, what are some things the calculator can and can't do that we haven't addressed yet? One thing that I don't believe we've addressed yet is using calculator shortcuts in order to deal with frequency tables. So that's the first one I want to do from this slide right here. So what we have here is some data that represents the length of book titles. So a one-word book title happened 3 times. A 2-word book table happened 9 times. A 3-word book table happened twice, etc., etc. So the actual list that this is summarizing is 1, 1, 1, 2, 9 times, 3, 4, 5, 6, 7, 8, 9, etc., etc. So based on what we've learned so far in the class with putting that in a calculator, actually let me get my calculator ready here. So I want to go to y equals, turn off that stat plot. I have no equations. Stat edit. Going to get rid of that old data. Zoom 9, clear out any weird window dimensions, and now we're good. Okay, so if we go to stat edit, we could put 1, 1, 1, 2, 2, 2, 2, 2, 2, etc., 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 all in L1, and then want to run our one variable statistics. If we have a frequency table, we can work with getting that frequency table basically as it appears here into our calculator. So in L1, I'm going to put 1, 2, 3, 4, 5. So that represents the actual numbers in our data list. Then L2 is going to be how often each one of those occur. Then I'm going to go to stat, calc, one variable statistics, and the list is L1. Prior to this problem, we've always had frequency list blank because everything was in L1. Now the frequency list is L2. So the calculator will read this as that table right there. Calculate. All right, a run through of what the calculator is telling us. X bar, that's the mean. That's the sum of all the items in the list, the sum of the squares. So if you're doing like a from scratch type of statistics formula, that would be a useful thing to know. These are our two measures of standard deviation. The S sub x, that's the one that's dividing by n minus 1. The sigma is the one that's dividing by n. That's for the sample, that's for the population. With the chapter we're in right now, we're always using the S sub x. That 1.11 number is what we want to be reporting. Okay, the last 5 numbers are the 5-number summary. So in terms of what they were asking us for here in the instructions, back this out a little bit here. Use your TI-84 to find a median. Oops. So that would be the 2. The mean, that was the first number in the list, that's about 2.35. The IQR, the calculator doesn't tell you directly the IQR. What you'd have to do is do the Q3 minus the Q1. So 3 minus 2 would give us the IQR. And then sample standard deviation. The sample standard deviation is the S sub x, not the sigma sub x. Now this particular little problem set here was kind enough to say sample standard deviation. Chances are in your textbook and on an AP exam, it's not going to say sample standard deviation. It's going to say standard deviation, and part of what you need to know is going to be which one you need to report using the correct symbols and stuff. All right, I'm not going to go through the whole final thing of the calculator keystrokes, just talk about in general. One of the data displays that we've done was stem and leaf plots. So what happens here is you put the left side of the number there, the right side of the number there. So our data set is 46, 53, 58, 59, 61, 62, 66, etc., etc., etc. There are no cool calculator shortcuts to get this into there. The only thing that could possibly happen is if you converted that into one of those, then you could use the calculator in terms of having less to type in. Normally that's more work than it's worth. If you need to find those things they're asking us for this data, you're pretty much forced into just going everything L1, 46, 53, 58, etc., etc., etc. Okay, another data display that we've used, dot plots or line plots. The two are interchangeable here. Again, there's no cool calculator shortcut for this. If you can translate this into one of those, now some dot plots you could easily do that, where it's the same number repeating over and over again, and you can get that into this, then you have yourself a nice shortcut in order to get your summary statistics. But this as is, you're pretty much forced into just typing it all in L1. 1, 2, 3, 3, 4, 5, 5, 6, blah, 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 blah. Get them all in. All right, I think that wraps up everything. Yep, that's the last slide for this PowerPoint.